When sizing breakers and feeders for meter banks and switchboards, the electrical code specifies that the breaker and feeder must be sized for 100% of the non-continuous load plus 125% of the continuous load and 25% of the largest motor load. The code does not require sizing the breaker and feeder to the meter banks based on 1.25% of the computed load, or limiting the load to no more than 80% of the breaker's rating using that method alone. For sizing a panel board, the same criteria applies. Size the panel board based on 100% of the non-continuous load plus 125% of the continuous load and 25% of the largest motor load. It is important to understand what constitutes a continuous load. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Examples of continuous loads include lighting in commercial buildings, heating systems that run for extended periods, and certain types of machinery. Non-continuous loads are loads that are not expected to operate for 3 hours or more. Examples of non-continuous loads include receptacle outlets, intermittent motor loads, and appliances that are used for short periods. When calculating the load for a feeder or service, it is essential to identify all continuous loads and apply the 125% factor. This ensures that the overcurrent protection device is adequately sized to handle the sustained current draw. Motor loads require special consideration due to their inrush current during starting. The National Electrical Code (NEC) requires that the feeder and overcurrent protection device be sized to handle the motor's full load current plus an additional percentage to account for the starting current. The specific percentage depends on the motor's design and the type of overcurrent protection device used. For example, NEC Section 430.22 typically requires conductors supplying a single motor used in a continuous duty application to have an ampacity of not less than 125% of the motor's full load current rating. This increased ampacity ensures that the conductors can safely handle the elevated current during motor startup, preventing overheating and potential insulation damage. Similar requirements exist for sizing the overcurrent protection for motor circuits, taking into account the motor's starting characteristics and the type of protective device, such as fuses or circuit breakers. Now, let's consider some examples to illustrate how these rules are applied. Imagine a small commercial building with a computed non-continuous load of 50 amps and the continuous lighting load of 40 amps. To determine the minimum feeder size, first calculate the continuous load contribution, which is 40 amps times 1.25, equaling 50 amps. Then add this to the non-continuous load of 50 amps, resulting in a total calculated load of 100 amps. Therefore, the feeder and breaker should be sized to handle at least 100 amps. Next, consider a situation with a motor. Suppose a workshop has a computed non-continuous load of 30 amps, a continuous load of 20 amps, and a motor with a full load current of 10 amps. Assume this is the largest motor. The continuous load contribution is 20 amps times 1.25, equaling 25 amps. The motor load contribution is 10 amps times 0.25, equaling 2.5 amps. Adding these to the non-continuous load of 30 amps gives a total calculated load of 57.5 amps. The feeder and breaker would need to be sized to handle at least 57.5 amps. In practice, you would select the next standard size breaker and conductor that meets or exceeds this calculated value. When applying these rules, it's important to consult the specific requirements of the NEC and any local amendments. The NEC provides tables and detailed instructions for calculating feeder and service loads, as well as for selecting appropriate overcurrent protection devices and conductor sizes. For example, NEC Table 310.16 provides ampacity ratings for various conductor sizes based on their insulation type and installation conditions. It's also essential to consider voltage drop when sizing feeders, especially for long runs. Excessive voltage drop can cause equipment to malfunction and reduce its efficiency. The NEC provides guidelines for limiting voltage drop in feeders and branch circuits. In addition to the NEC, local jurisdictions may have their own electrical codes and regulations that must be followed. These local codes may be more stringent than the NEC in some areas, so it's crucial to be aware of and comply with all applicable requirements. Regarding the question about fuses, a fuse can always be considered a 100% rated device. This means that a fuse is designed to carry its rated current continuously without tripping. However, it's important to select the appropriate fuse for the application based on the circuit's characteristics and the equipment being protected. Fuses are available in different types with varying time current characteristics. Some fuses are designed to trip quickly in response to overcurrents, while others are designed to provide a time delay to allow for temporary overloads, such as motor starting currents. The selection of the proper fuse type is critical to ensure adequate protection and prevent nuisance tripping. For example, a time delay fuse may be appropriate for protecting a motor circuit, while a fast-acting fuse may be better suited for protecting sensitive electronic equipment. When replacing fuses, it's essential to use the same type and rating as the original fuse. Using a fuse with a higher rating than specified can create a safety hazard and damage equipment. Always consult the equipment manufacturer's instructions or a qualified electrician for guidance on fuse selection. In summary, when sizing breakers, feeders, and panel boards, it is essential to consider both continuous and non-continuous loads, as well as any motor loads. The NEC provides detailed rules and guidelines for calculating these loads and selecting appropriate overcurrent protection devices and conductor sizes. Fuses can be considered 100% rated devices, but it's crucial to select the correct fuse type and rating for the application. Always consult the NEC and local electrical codes, and seek the advice of a qualified electrician when necessary to ensure safe and compliant electrical installations. The proper application of these principles is critical for maintaining electrical safety and ensuring the reliable operation of electrical equipment. Remember to factor in all applicable loads according to the NEC, not to overload your panel boards or breakers by performing a correct load calculation, and most importantly to have safety in mind. Let's talk about the different types of circuit breakers that are commonly used in electrical systems. Firstly, there are standard thermal magnetic circuit breakers. These are the most common type found in residential and commercial applications. They use a bimetallic strip that bends when heated by an overcurrent, tripping the breaker. They also have a magnetic element that trips the breaker instantly in response to a short circuit. Secondly, ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. These breakers constantly monitor the current flowing in the circuit and trip if they detect an imbalance, indicating that current is leaking to ground. GFCIs are required in areas where there is a risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Thirdly, arc fault circuit interrupters, or SIs, are designed to protect against arc faults. These breakers detect the unique signatures of arcing faults, which can be a fire hazard, and trip the breaker to interrupt the circuit. SIs are required in many areas of the home, particularly in bedrooms. Fourthly, there are molded case circuit breakers. These are typically used in higher current applications in commercial and industrial settings. They have a robust construction and can handle larger fault current. Fifthly, insulated case circuit breakers are similar to molded case breakers but offer even higher levels of insulation and protection. They are used in critical applications where safety and reliability are paramount. Sixthly, there are high voltage circuit breakers. These are used in substations and other high voltage applications to protect equipment and interrupt fault currents. High voltage breakers use various technologies to extinguish the arc that forms when the breaker opens, such as oil, air, or vacuum. Understanding the different types of circuit breakers and their applications is essential for designing and maintaining safe and reliable electrical systems. Always consult the NEC and other applicable standards when selecting and installing circuit breakers. Continuing on, let's explore the different types of fuses and their applications in electrical protection. Firstly, there are cartridge fuses, which are one of the most common types. They consist of a fusible link enclosed in a cylindrical cartridge, typically made of glass or ceramic. Cartridge fuses are available in a wide range of voltage and current ratings and are used in various applications. Secondly, plug fuses, also known as Edison base fuses, are commonly used in older residential electrical systems. They have a screw-in base similar to a light bulb and are designed to protect against overcurrents in branch circuits. However, plug fuses are less common in modern installations due to their limited interrupting capacity. Thirdly, blade fuses, also known as knife blade fuses, are typically used in higher current applications such as in industrial equipment and distribution panels. They have a blade-shaped terminal that provides a secure connection. Fourthly, time delay fuses, also known as dual-element fuses, are designed to withstand temporary overloads such as motor starting currents without tripping. They have a time delay characteristic that allows them to carry short-duration overcurrents without interrupting the circuit. Fifthly, current-limiting fuses are designed to quickly interrupt high-fault currents, limiting the amount of energy that flows through the circuit during a fault. They are used in applications where high-fault currents are a concern, such as in industrial power systems. Sixthly, semiconductor fuses are specifically designed to protect sensitive semiconductor devices, such as diodes and thyristors, from overcurrents. They have very fast response times and precise current limiting characteristics. Seventhly, there are Class CC fuses. These are compact, current limiting fuses that provide a high level of protection for control circuits and other sensitive equipment. Eighthly, Class J fuses are also current limiting fuses but have a higher interrupting rating than Class CC fuses. They are commonly used in industrial applications. Ninthly, Class R fuses are time delay fuses that provide both overload and short circuit protection. They are commonly used in motor circuits. Choosing the appropriate fuse type and rating is crucial for ensuring adequate protection and preventing nuisance tripping. Always consult the equipment manufacturer's recommendations and the NEC when selecting fuses. To further clarify the application of these rules, let's consider some specific examples related to residential and commercial electrical systems. In a residential setting, imagine a new kitchen is being added to a home. The electrical load for the kitchen includes lighting, small appliances, and a refrigerator. The lighting load is estimated to be 600 watts. The small appliance load is calculated as two 20-ampere circuits at 120 volts each, totaling 4,800 volt amperes, and the refrigerator is rated at 6 amps at 120 volts, or 720 volt amperes. To determine the total load for the kitchen, we need to apply the demand factors specified in the NEC. For the small appliance circuits, the NEC allows a demand factor of 75% for loads exceeding 3000 volt amperes. Therefore, the demand load for the small appliance circuits is 3000 volt amperes plus 75% of the remaining 1800 volt amperes, which equals 4350 volt amperes. Adding the lighting load of 600 watts, the refrigerator load of 720 volt amperes, and the small appliance load of 4350 volt amperes gives a total load of 5670 volt amperes. The current is then calculated by dividing the total load by the voltage. This equals 47.25 amps. The feeder to the kitchen should be sized to handle at least 47.25 amps. In a commercial setting, consider a retail store with a total lighting load of 10,000 volt amperes, a receptacle load of 5,000 volt amperes, and an air conditioning unit with a full load current of 20 amps at 208 volts, which equates to 3,460 volt amperes. The NEC allows demand factors to be applied to the lighting and receptacle loads based on the type of occupancy. Assuming a demand factor of 50% for the lighting load and 100% for the receptacle load, the total lighting load is 5000 volt amperes, the total receptacle load is 5000 volt amperes, and the air conditioning load is 3460 volt amperes. Summing these loads gives a total load of 13,460 volt amperes. Dividing by the voltage of 208 volts and adjusting for three-phase power by multiplying by the square root of 3 yields a current of approximately 37.4 amps. The feeder to the retail store should be sized to handle at least 37.4 amps. When performing these calculations, it's important to consider any future expansion or additional loads that may be added. It's always a good practice to oversize the feeder slightly to accommodate future growth. The NEC provides detailed guidance on load calculations and demand factors for various types of occupancies. Always refer to the NEC and consult with a qualified electrical engineer or electrician when designing and installing electrical systems. Let's delve into the nuances of continuous and non-continuous loads, providing a clearer understanding of how they impact electrical system design. A continuous load, as defined by the NEC, is a load where the maximum current is expected to continue for 3 hours or more. This definition is crucial because it dictates how the overcurrent protection device and conductors must be sized to prevent overheating and ensure safe operation. Examples of continuous loads include continuous lighting in office buildings, large retail spaces, and industrial facilities. These lighting systems often operate for extended periods, exceeding the 3-hour threshold. Another example is heating systems in climates where heating is required for most of the day. Similarly, large motors that drive continuous processes, such as pumps in a water treatment plant or conveyors in a manufacturing facility, are also considered continuous loads. In contrast, non-continuous loads are those where the maximum current is not expected to continue for 3 hours or more. Examples of non-continuous loads include receptacle outlets in homes and offices, which are used intermittently for powering various devices. Appliances such as washing machines, dishwashers, and microwave ovens are also considered non-continuous loads, as they operate for relatively short durations. Intermittent motor loads, such as those found in power tools and some HVAC systems, also fall into this category. The distinction between continuous and non-continuous loads is critical because the NEC requires that continuous loads be multiplied by a factor of 1.25 when calculating the feeder and service size. This 125% factor is applied to the continuous load to ensure that the overcurrent protection device is not loaded to more than 80% of its rating. This rating provides a safety margin to prevent the breaker from tripping unnecessarily due to prolonged high current draw. When designing an electrical system, it's essential to accurately identify all continuous loads and apply the 125% factor. Failure to do so can result in undersized conductors and overcurrent protection devices, leading to overheating, nuisance tripping, and potentially dangerous conditions. Consider a scenario where an office building has a continuous lighting load of 80 amps and a non-continuous receptacle load of 40 amps. To calculate the minimum feeder size, we first multiply the continuous lighting load by 1.25, which equals 100 amps. Then we add the non-continuous receptacle load of 40 amps, resulting in a total calculated load of 140 amps. Therefore, the feeder and overcurrent protection device must be sized to handle at least 140 amps. If the continuous load had not been properly identified and the 125% factor applied, the feeder could have been undersized, potentially leading to problems. Remember that the NEC provides specific guidelines and tables for calculating feeder and service loads, including demand factors that can be applied to certain types of loads. It's important to consult the NEC and other applicable standards to ensure that electrical systems are designed and installed in accordance with all applicable requirements. Now, let's further consider the impact of ambient temperature and conductor dirting on conductor ampacity. The ampacity of a conductor, which is its current carrying capacity, is affected by the ambient temperature in which it is installed. High ambient temperatures reduce the conductor's ability to dissipate heat, which in turn reduces its ampacity. The NEC provides tables that list the ampacity of conductors based on their insulation type and temperature rating, as well as correction factors for adjusting the ampacity for different ambient temperatures. For example, NEC Table 310.16 lists the ampacity of conductors based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to reduce the conductor's ampacity. Similarly, if multiple conductors are bundled together in a conduit or cable, their ampacity must be derated to account for the increased heat buildup. The NEC provides adjustment factors for different numbers of conductors in a raceway or cable. These adjustment factors reduce the ampacity of each conductor to prevent overheating. Consider a scenario where 3 current-carrying conductors are installed in a conduit in an area with an ambient temperature of 40 degrees Celsius. The conductors are insulated with THHN insulation, which has a temperature rating of 90 degrees Celsius. According to NEC Table 310.16, a 12 AWG THHN conductor has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius. However, since the ambient temperature is 40 degrees Celsius, a correction factor of 0.88 must be applied, reducing the ampacity to 26.4 amps. Additionally, since there are 3 current-carrying conductors in the conduit, an adjustment factor of 0.8 must be applied, further reducing the ampacity to 21.12 amps. Therefore, the 12 AWG THHN conductor can only carry 21.12 amps in this scenario without exceeding its temperature rating. It's important to carefully consider ambient temperature and conductor rating when sizing conductors to ensure that they can safely carry the intended load without overheating. Failure to properly account for these factors can result in undersized conductors, leading to insulation damage, nuisance tripping, and potentially dangerous conditions. Always consult the NEC and other applicable standards for detailed guidance on conductor ampacity, correction factors, and adjustment factors. Let's explore some of the common misconceptions regarding electrical calculations and NEC requirements. Firstly, there is a misconception that you can always round up to the next standard size breaker or conductor. While it is permissible in some cases, it is not always allowed and can lead to safety issues if not done correctly. The NEC specifies when rounding up is permitted, and it typically applies to specific situations such as motor circuits or when the calculated load falls between standard breaker sizes. However, it is generally not allowed to round up the conductor size beyond what is necessary to carry the calculated load, as this can lead to overprotection and nuisance tripping. Secondly, there is a misconception that demand factors can be applied indiscriminately to all types of loads. Demand factors are intended to account for the fact that not all electrical loads operate at their maximum capacity simultaneously. However, demand factors are specific to certain types of occupancies and loads, and they cannot be applied arbitrarily. The NEC provides specific demand factors for various types of loads such as lighting, receptacles, and appliances, based on the type of occupancy such as residential, commercial, or industrial. It is important to consult the NEC and apply the appropriate demand factors for the specific situation. Thirdly, there is a misconception that the 80% rule applies to all overcurrent protection devices. The 80% rule, which states that a circuit breaker or fuse should not be loaded to more than 80% of its rating, applies primarily to continuous loads. Continuous loads are defined as loads where the maximum current is expected to continue for 3 hours or more. For non-continuous loads, the 80% rule does not necessarily apply, and the overcurrent protection device can be loaded to its full rating. Fourthly, there is a misconception that ground fault circuit interrupters, or GFCIs, are only required in wet locations. While GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas, they are also required in other locations where there is a risk of electric shock, such as construction sites and healthcare facilities. The NEC specifies the locations where GFCIs are required, and it is important to comply with these requirements to ensure electrical safety. Fifthly, there is a misconception that arc fault circuit interrupters, or FSIs, are only required in bedrooms. While FSIs are required in bedrooms to protect against arc faults, which can be a fire hazard, they are also required in other areas of the home such as living rooms, dining rooms, and family rooms. The NEC has expanded the requirements for FSIs in recent years to provide greater protection against arc faults throughout the home. Avoiding these common misconceptions and adhering to the NEC requirements is essential for designing and installing safe and reliable electrical systems. Always consult the NEC and seek the advice of a qualified electrical engineer or electrician when in doubt.